Hello and welcome to your stats videos. All right, so this is just a practice sheet for hypothesis testing. There's a lot that goes into one of these, so I figure the more practice, the better. All right, let's take a look at number one. 11% of the products produced by an industrial process over the past several months have failed to conform to specifications. The company modifies the process in an attempt to reduce the rate of nonconformities. In a random sample of 300 items from a trial run, the modified process produces 16 non-conforming items. Do these results provide convincing evidence that the modification is effective? Support your conclusion with a test of significance. All right, so our hypothesis. The null is that this change has made no difference. All right, the null is always your statement of no difference. So it would be that the proportion still equals 11%. The alternative is that our new process has improved it. And since we're measuring the rate of non-conformities or the ones that kind of fail, we're going to say that this has decreased and is now less than 11%. All right. We have no reason to use anything else, so we're going to stick with our standard alpha level of 0.05. Now, before we actually do this, we should consider whether or not our conditions are going to be met. So it does tell us that we used a random sample. We kind of are left to assume that 300 items is less than 10% of the population. And given our sample size of 300 and the failure rate of 11%, we have at least 10 expected successes and 10 expected failures. 11% times 300 is 33. 89% times 300 is 89% times 300 is 267. So our conditions are met. Next, we're going to calculate our test statistic, and we're going to use the calculator to help us do this. So we're going to go to stat tests, 1 proportion z-test. So let's put that up here so that we know what we're doing. 1 proportion z-test. All right. Our null is that it's 11%. So p sub 0, we're going to put in 11%. The number of successes in this problem was stated to be 16. So change that right there. Our sample size was 300. All right, so we can change that right there. And we are checking to see if we are now less than 11%. All right, so that's just kind of showing me everything that you chose in the calculator. All right, now when we do that, we get a test statistic. So our test statistic from this result is negative 3.13. We'll say 7. All right, we get a p-value. All right, now be careful with this p-value because there is an e there. All right, so this is actually 0.000854. And then based on this p-value, we have to write a conclusion. So what we would say is, because our p-value is less than our alpha, we reject the null and accept the alternative. All right, which in this case is suggesting that we found enough evidence to say that these improvements do help. All right. So what we found in our sample was outside of what we would expect from random variation. It was a large enough decrease because, again, 16 out of 300 was 5%. Right? So this 16 out of 300 was basically 5%. So that was a big enough drop that we are fairly confident that the true rate of failure is now going to be less than 11%. All right. So let's take a look at another one. Nationally, the proportion of red cars on the road is 12%. A statistically minded fan of the Phillies wonders if fans are more likely to drive red cars. One day during a home game, he takes an SRS of 210 cars parked at Citizens Bank Park while a game is being played and counts 35 red cars. There are 21,000 parking spaces in total. Is this convincing evidence that the Phillies fans prefer red cars more than the general population? All right. So again, we got 35 out of 210 in our sample. All right. Let's see. 35 out of 210 is like, 16.7%. Is this 16.7% different enough from this 12% that we can be confident that Phillies fans purchase more red cars? Or is that sort of in the realm of random variation? All right, so again, our null is going to be that the population parameter is still 12%. It's the statement of no difference. We are testing to see if Phillies fans prefer red cars. So our alternative is going to be that P is greater than 12. All right, again, no reason to use anything different. So we're going to stick with our alpha of 5%. Now, if we sort of run through the conditions here, they tell us how many parking spaces there are, and 210 is less than 10% of this number. So we're okay there. We have to expect at least 10 successes and 10 failures. So 0.112 times 210, and then 0.88 times 210. Both of those are above our thresholds, so we're fine there. And it does tell us that we're taking a random sample here. So all of our conditions are in place. All right, obviously the cars are going to be like independent of one another. What one person is buying, one car is not the color of one car doesn't influence the color of the car next to it, and so on and so forth. So we also have that in place. So that brings us to, again, using the one proportion z-test. All right. Our starting null value is 0.12. It's our starting parameter value. All right. This time it tells us that we found 35 red cars, so that would be our x. Our sample size was 210, also coming from the problem. And this time we are checking to see if we are greater than the null value. All right, so if I go to stat tests, one prop z test, I'm going to change this to 12, change this to 35, change this to 210, and this time we're doing a greater than. All right, I get a test statistic of 2.08. I get a p-value of 0.0187. And then this p-hat is just this 167 that we already calculated. So here's our p-value. And from this, we can write our conclusion. All right. So same conclusion as the first one, actually, because our p-value is under our alpha of 5%. We reject the null. and accept the alternative. Which in this case, given the setting that we're looking at, seems to be that Phillies fans do prefer red cars. All right, that's what we were able to conclude, because again, this value that we got was statistically unlikely given this assumption. All right, it only had effectively a 1.87% chance of happening. So if we have to choose between, did we get unlucky and end up with something that only happens about 2% of the time, or is this conclusion wrong? The safer bet is to say that this conclusion is wrong, because this only had a 1% or 2% chance of happening. All right. So let's take a look at the back now. All right. Do political attack ads work? A congressional candidate who currently has the support of only 44% of the voters runs a television spot that aggressively attacks the character of an opponent. To determine whether the advertisement changes his support level, his pollsters conduct an SRS of 450 voters and find that 186 support the candidate. This produces a 95% confidence interval for the proportion of voters who support him. All right. Suppose his pollsters conduct a test of p.44 against the alternative p is not equal to 0.44 using a 5% alpha. Use the confidence interval to determine whether the test would reject or fail to reject the null hypothesis. All right. So this interval represents the possible values of p. And if we notice, 44% is inside of that interval. So because 44% is inside of that interval, it's a possible value, which means we cannot reject this null hypothesis. We can't reject and say this isn't true, because it does fall inside of our interval. So we would fail to reject the null because 44 falls inside of our interval. All right. Find the p-value for the test described in part A. Explain what it measures in the context of the problem. You do not need to present a complete significance test. All right. So I'm just going to go here to stat tests, one prop z test, because this is the quickest way to get the p-value. I'm going to change my proportion to 44%. I'm going to say that I got 186 out of 450 from my sample. And this time we're doing a not equal to. All right. And then we're going to calculate, and we get a p-value of 0.2545. And again, this came from doing a one prop z test where we made p sub 0 0.44. We used an x of 186. We used an n of 450, and we did a not equal to p sub 0. All right. So what does this represent? All right. Basically, it says, there was a 25% chance of getting a sample proportion of, now let's see, what is, okay. Sample proportion was 41%. All right, that's just the 186 divided by the 450. So of 41%, and again, this is just the 186 divided by 450. So there's a 25% chance of getting a sample proportion of 41% when the sample size was 450, assuming the population parameter is 44%. All right, so it's not like this 25% is just, oh, you had a 25% chance of getting this no matter what. It's saying, all right, if the null is true and you take a sample of 450 people, then there is a 25% chance of getting the sample result that we received or something more extreme. All right, but that's kind of what that's telling us there. Number 4, the germination rate of seeds is defined as the proportion of seeds that, when properly planted and watered, sprout and grow. A certain variety of grass seed usually has a germination rate of 80%, and the company wants to see if spraying the seeds with a chemical that is known to change germination rates in other species will basically change the germination rate in grass species. They spray 400 seeds with a chemical, and 307 germinate. This produces a 95% confidence interval for the proportion from 0.726 to 0.809. Suppose they conduct a hypothesis test of p equals 0.8 against the alternative p does not equal 0.8. Use a confidence interval to determine whether the test would reject or fail to reject. So pretty much the same question as above, just different numbers. And again, all right, this 80% is inside this interval, which means we're unable to reject the null. All right, so we would fail to reject the null because 0.8 falls inside the confidence interval. All right. Part B, find the p-value for the test described in Part A. Explain what it measures in the context of the problem. All right, so again, same thing we did up above, just different numbers. We're still using one prop Z test. This time our p sub 0 is 0.8. Our x is, where is it? 307. Our n is 400. And this time we are testing against not equal to p sub 0. All right, so stat tests, one prop Z test. All right, this gets changed to 0.8. This gets changed to 307. This gets changed to 400. We're sticking with the not equals to. We hit calculate, all right, and we get a p-value of 0.1042. And again, the interpretation is there was, I'm just going to say roughly a 10% chance of getting a sample proportion of, let's see, what was our sample proportion? 76.75 or more extreme. When using a sample size of 400, and this is the big part, if the population parameter is truly 0.8. All right, so if the population parameter is truly 0.8, there was a 10% chance of getting a result similar to what we saw, this 307 out of 400. Again, that's where this is coming from. And because of that, it's above our threshold, so we would sort of fail to reject the null. All right. So again, hopefully this is helpful. Again, the idea is you have a starting point, you gather data, and then you're basically saying, all right, is this data that I gathered far enough away from this starting point that I can be reasonably confident that my starting point is wrong? All right. And if it's not far enough away, then we say, we're not convinced that our starting point is wrong. We're not saying that it's right. We're just not convinced that it's wrong. And if it is far enough away, then we can say, hey, it's wrong. I'm accepting this alternative. Hey, it's wrong. I'm accepting this alternative. Or, it's too close. I'm failing to reject this premise. Or, it's too close. I'm failing to say that this is wrong. It might be wrong, but I don't have enough evidence to say that it is one way or another. All right. So hopefully this was helpful. If you have any questions, let me know, and we'll go from there. All right.